5, 4, 3, 2, 1. Engines full power. And liftoff.
While the ongoing competition to launch the world's next best rocket tends to dominate news headlines, there's a little-known mission at NASA to develop a new kind of space telescope. And this project is using something else entirely: balloons.
So it seems like a pretty cool idea. Build a telescope, put it on a balloon, get out of the atmosphere. But that's actually kind of hard. Yeah, it's freaking terrifying. Because all the, like, and also almost every flight I've had has had those moments where you think this thing has failed. Like, it's gone wrong. There's nothing, well, there's kind of a general principle. We don't fly it if it's not necessary. And so every single thing on this payload and every decision we make could turn out to be the choice between the experiment working or failing.
Oh, they're stuck.
Let it go.
Release it.
Go forward. Stop.
You're fucking kidding me.
So yeah, what could go wrong? A lot of things could go wrong.
There's a lot of single point failures in SuperBIT.
That gyroscope we bought, is it gonna work?
Gyroscopes have to work. Like, there's two sets of gyroscopes.
If one of them fails, it's like losing one of our senses.
So did we consider all of the possibilities when we wrote the flight software?
We're testing it as we speak right now.
There's a camera link cable that does not like to get cold because the temperature change in the stratosphere, right? It's minus 50.
Is the heater right? Is it got enough power to heat when we need to heat?
We have put heaters around it. We've wound wire literally around this cable.
It will have to make sure that every single cable is where it's supposed to be.
Oh, did we nick the wire? Is it gonna come loose? And if it does, the experiment fails. And it just keeps on going at every step.
Did I measure the quantum efficiency correctly?
Yep, I'll get it. Wait.
I hope so.
Is the primary mirror really as good as the vendor says it is? I hope so.
It's like, how do we change it? Move the mirror back and forth. How do you move? There's 3 motors, it's not just one. Okay.
If one of them were to fail, we'd be in hot water.
The ability for the camera to take pictures, make sure it works.
Because if it doesn't, the experiment fails.
That is, in essence, ballooning. We need to make sure everything is correct.
Yeah, it's not working. It's not connecting it. So check the power.
Yep.
Okay, I'll check the logs. Most of the struggle we're having right now is trying to run this thing in the lab when it was designed to run in the stratosphere. Good, I like that step. Do it again. Finding the fake star with this kind of wobbly mount, which there's no finding fake stars in flight because they aren't fake.
Okay.
All right, there it is.
Okay, do you need any more collimator moves?
No.
Okay, we found it. I thought it would take longer, but sometimes you get lucky.
So telescopes want to look at space, but they have to look through the air. And if you've ever seen, a mirage or, a guy on a hot road and he's kind of shimmering, that happens when you look at stars. And so you're limited in the resolution you can get on a ground-based telescope. So the obvious answer is to get into space, get out of the atmosphere. But building a telescope that can operate in space, that can survive the launch, that can have the reliability needed for these sorts of things is incredibly expensive. So balloon-based telescopes kind of fit in between. They're far less expensive than a space-based telescope, but they get out of the atmosphere, you get you that extra resolution you can't get from the ground.
So SuperBIT is a balloon-based imaging telescope. This telescope right here will actually be going to Wanaka, New Zealand, where it will be attached to NASA's super pressure balloon. And that balloon is by volume even bigger than the size of a football stadium. That balloon will fly up to 30 or 40 kilometers up in the stratosphere. That is 3 to 4 times higher than normal commercial planes go.
Telescope, you want to build a telescope with this incredible resolution, but it's going to hang from a rope. So what do you got to do? Obviously you need to have a telescope that's going to be able to take the images. You need to be able to hold the telescope stable and point it where you want. And that turns out to be a real challenge because you're hanging from a rope. Then you got to take that, you need to be able to control the telescope from the ground. You need communications, you need automation. You need to be able to store the data on the payload and then get it all down again. There's a lot of steps to making something like this work.
And it goes. Oh, and it goes. Man. Oh, jeez. Bye-bye, Bit. Goodbye, Bit. Bye-bye. Oh, my God.
Go! Well, we had to remake a bunch of the components after the last crash.
Constructing electronic subsystems for motor controllers.
The solar panels, which have to be custom made for us.
Writing code for the science camera on how to command it, how to operate it.
Actuators to move the main mirror. So we want to move all 3 mirrors.
Measuring the optical sky background levels from previous flight data. And this has never been done before.
A lot of the cables, which is, space cabling is kind of an expertise.
The sensitivity or the quantum efficiency of the sensor, which also hasn't been measured before. And both of these things are really important because they limit how dim of a source that the instrument is able to observe.
By far, probably my favorite thing to work on SuperBIT was the ability to put it in an autopilot mode. It takes into consideration where SuperBIT is at that moment in time, what it can look at, and then it takes images based on priority that we've preset.
Easy to say, but hard to do. This experiment is incredibly complicated. And there's a general rule of thumb. If it hasn't been tested, it doesn't work.
So it says 0 here.
Okay, so something went wrong. Okay, is it still moving?
Are you expecting it to go down?
I think so, yeah. But it's okay.
I see a little part that fell out.
Yeah, scrape the top of this in.
This is probably that.
Not cool.
Great.
All right, we'll try and get the other side out, and we'll figure out what's going on.
All right.
Whenever something goes wrong, it's just absolute panic. In my mind, I pretend to be fine. In fact, I'm dying inside.
Yeah, likewise.
It'll work. Yeah, because we found an obvious problem, and it just wasn't in the right place. So what I don't understand is how it could be not in the right place.
That is the question.
Okay. So it's really important for us to stabilize our image. When we're taking a long exposure, we need to keep the stars exactly fixed on the camera. Otherwise, they're just going to move around and blur the image. And so that's what our image stabilization system is for. We have this mirror in there, which is on an actuator that can move very, very fast to correct for any motions of the telescope. The trick, of course, is to know how much did the telescope move. So to do that, we have 2 stages. The first stage is these gyroscopes. These are very, very sensitive gyroscopes, can measure extremely small motions of the telescope. And if they detect the telescope has moved, then the computer will tell the mirror to move to counteract that, to keep the star exactly centered. These gyroscopes are not great at lower frequencies. They can kind of drift around a bit. So to supplement them, we have a second set of cameras. You can't see them here, but they're inside the optics box, which will track a particular star and report back to the computer how much the star has been moving, kind of to correct for those drifts. The combining those 2 things, we can know exactly where our star is versus time, and then the image stabilization mirror can correct for it. And so we can get that incredibly exquisite image stability we need for these images. To do a correction, I need to know where I'm looking.
Sure.
Right, so right now, how far off is the star? That's what I need to know.
From the centroid.
Yeah, from where I want it to be. I want it to be in the center of this pixel.
Mm-hmm.
Where is it? Okay, we need to look at the code. Man, I always get to this state where I have to start thinking.
Yeah.
And my first thought is this horrible reflexive desire to go get coffee. I know. Thinking is painful.
That's why I come prepared.
Thinking is painful. I'll go get coffee.
It's after 2 p.m. though. Don't they say you can't sleep after
whatever.
2 p.m.?
I don't want to sleep. I want to work. The question is, what's the architecture? What's actually going on in the code? We may need to do some significant upgrades to the code.
So it's off by like
Oh,
30
right.
pixels.
Oh, shoot. Oh, that was a code change I had to make. Oh, I forgot about that.
To make the amplitudes the same.
Yes, because right now, I think there's only one plate scale. Like something switched.
Yeah. Oh, maybe it's this? No, that's just power. I expected it to just work, but it didn't. But I'm not surprised because we've changed a few things from the 2019 flight. Specifically, the mount is now located at a different place. So like all the signs of the FGS are basically, they don't agree with each other anymore. So we're just trying to fix that. Oh, they're matching. Nice. Very nice. Okay, so we'll change the gyro too. Okay.
Yes,
Okay.
but not in the code.
Yep.
Okay, so should we try this thing? Can we
Let's
make
do
it
it.
work? Okay, so you're pushing at it, and I definitely see the star like it's moving like by 10 pixels.
Okay.
That's perfect. Oh, look at that. Yeah, that's crazy. Yeah, same thing. You're moving it back and forth by a bunch.
Uh-huh.
And then when I enable it, boom, motion goes away. All right, I think we're good. We finished testing the image stabilizer last night, and so today was the day we were going to get it all put together. So we picked it up, and the first thing when we got over here, we discovered that it was very, very back heavy.
There's a bit of a problem here.
Yes, what's the problem?
Give me 1 second.
Yeah, is it too hard or is it okay?
It is heavy, but... No, that's moving the whole... How far back is it right now?
It's quite back. It's too back heavy. So we just need to move the telescope forward in the dove plates. But that's a challenging job. It's designed to be possible, but also not designed to be easy. This piece, these screws go through. The top comes loose.
Uh-huh, too small, right?
So we had to pound the telescope forward. Now the telescope is pretty well balanced, front and back. Now we're trying to put it into the middle frame, and the bolts aren't lining up. And we're not exactly sure why they're not lining up. It could be flexure in the frame.
Or maybe
It could be that the pieces are slightly different and they're just put in backwards. Or, I don't know. So it's close. It's like with a millimeter off, so it's kind of annoying. I'm sure we'll solve it when we're not feeling 9:15 at night. I think I need my coffee cup. Because there's coffee in it. Huh? I need my coffee cup for inspiration. So we spent the last couple of weeks since we came off the table and put the inner frame in the middle frame. We spent the time mostly getting all of the heater and thermometry system working. There's 50 heaters and over 100 thermometers on the payload. And so getting all those things, like masses of cables and wires, getting them all wired up, working, tested, verified, routed properly, each one is an easy job, but then when you have so many signals, it just takes a while to get them all right. Okay, can you look in those holes and see if they line up?
I did.
Are they perfect or
good.
no? Like
This one's
we want to come this way a little bit.
Yeah.
We're
Bent
bent this way.
Yeah, I don't think we're going to be able to move it this way because these bolts are already...
Oh, yeah, yeah.
Is it going in straight?
Yeah, looks like it.
Yep.
The other end on the solar panels.
Yep.
And then what's preventing them from rotating is the
Struts.
tubes.
Yeah. So that is, you take the tube, you stick it in a vise, close it till it's flattened, and then bend it to the right angle. All right. So here we have the SuperBIT telescope mounted in the stabilization mount, and the idea here is that when the payload is hanging from the balloon and swinging back and forth, you want the telescope to remain completely stable. Well, how stable? Well, the SuperBIT pointing system can hold SuperBIT stable to about a half of an arc second. How can we picture that? Imagine you're trying to thread a needle, but the needle is actually 2 football fields away, and you need to point well enough to keep the thread right through that needle, 2 kilometers away. That's how well SuperBIT can hold the telescope still, which is kind of impressive, but actually it's not good enough. We need to do 10 times better than that. So at the camera, we have a second image stabilization mirror, which can stabilize the image another factor of 10. So that's now kind of like trying to thread a needle that's 2 kilometers away or 20 football fields away. We have motors here for pitch and there for roll, which can be used to control the exact pointing of the telescope. Besides the motors, we have the roll star camera here, and on the other side we have the boresight star camera. These two are taking images of the sky, finding a bright star, and then reporting how much the star is moving to the master control computer, which can then take that information and feed back to the motors. And so we can keep a star centered in 1 pixel on the camera. Right now, we're in the process of putting it all together. Once that's done, we'll be putting the cap on and then hanging the whole thing from the hoist. We'll be opening up the overhead doors and looking out into the sky to verify that the pointing system has the stability that we need it to for flight.
We're trying to find a star on the science camera, but we're not able to find it. But we're able to find it on the tracking camera. So, not sure what's going on.
Nothing.
It's pretty cloudy now.
Is it cloudy?
Yeah.
Okay. We're not seeing anything. Let's go a couple more steps, but. There's just nothing there.
Yeah.
Oh boy.
Like that's really nothing.
Yeah.
That's a whole lot of nothing. High quality, nothing.
You want to try a different focus? Full 60s.
Mode 4? Nope.
Am I imagining that ring? Yeah, I see it too.
Mm-hmm. Huh. Maybe.
It looks closer to something.
No, that looks like it's an old picture, accidentally. I don't know if it's a star, but I don't think it's dark frame.
But it can't be that big, even if it's out of focus.
Oh, it sure can. Okay, let's get this thing shut down. You can turn the lights back on. The pointing system works pretty well. The tracking cameras worked beautifully, and we're not able to focus the primary telescope on the stars out the window. Don't know if that's because we just couldn't find the focus position yet, because there were clouds in the way, or possibly because the telescope range of focus doesn't get us into focus. So we'll have to try this again in the future. But all in all, it was a reasonably good night. And I need to leave now so I don't miss my subway. Okay, let's go to the yaw tab and see what it's doing. Okay, it's tracking really nicely. That's good news.
Yep.
That's really good. That's really good.
It's going pretty fast.
Yeah, it should be. It's speeding up to a full 4 degrees per second, then it'll turn around and slow down again. This is
So yesterday, bore and pitch were fine, but not yaw.
yeah.
And yaw still is worse.
Everybody's fine, like 1.4. I'm quite happy with this. Now, let's try and find out what the heck is going on with our illustrious science camera.
Yes.
Yep, and we see, as expected, absolutely nothing. And, you know, if it doesn't find it, then we gotta do some serious shrugging.
I mean, can we not just take a 30-second full frame first and look?
Oh, we did yesterday, and nothing changed.
Let's give it a shot.
We did it yesterday.
But if you can't find it in the full frame, is the autofocus gonna... Oh, I guess it will focus it so that we can find it in the full frame.
So yesterday you didn't autofocus?
We did, but it wasn't enough range. It was too big of steps, and it was.
Okay.
I think we're going to try this. I'm not willing to promise it's going to work.
If you don't win, then.
I'll be the one that have to go in there, adjust M1 manually.
I say 8 point.
Oh, holy crap! Woo! Here.
That's something not a hot.
Where was that?
Looking.
That was around -7.
Where is it?
Yeah.
It's right there.
Oh, it's fantastic. Okay, that's good. The telescope works.
That's great.
That's
Images for.
that's
Don't
not.
have to go,
But the telescope works. It can focus. The telescope can focus. That's not bad news. I was kind of worried about this.
Me too.
But remember how big I said the blob would be?
It was pretty much that big.
Yeah, no, that's pretty good.
So I think we can vibrate some solar panels tomorrow morning with the
We
wind.
don't need the night sky for that.
Nope.
Okay. Yeah.
Guys, let's go to Texas.
Yep.
Get the whip! Get the whip! Be careful on the sides.
The biggest thing that I hope that both of these telescopes, SuperBIT here and then eventually Gigabit, can help promote is accessible astronomy.
The ability to do wide field observations at high angular resolution is extremely powerful, from the near ultraviolet to the near infrared. There's so many science cases in stellar astrophysics, in galactic astrophysics, in extragalactic astronomy, in cosmology, learning about globular clusters, dark matter, dark energy, that observations like that can answer.
Hubble is a $15 billion project. That is a lot of money. Although it provides for really good science, but it is also oversubscribed with a lot of requests from a lot of different universities and researchers.
The idea of launching a balloon is that it's cheap. It doesn't take that much time, so that you can launch something, get it back, and fix problems, improve, make it better.
It could be a game changer in astronomy because it would allow low-cost, high-resolution, wide-field observations that will get you comparable science to these flagship missions, but at much faster timescales. You can do one every year.
Creating these cheaper telescopes, cheaper but better telescopes that operate from the stratosphere, that both take away the negative aspects of ground-based telescopes and the cost of a space-based telescope. So you're in the best of both worlds over there. That is something that I hope to prove with SuperBIT and then eventually with Gigabit as well.
I think the chances that this is a success are pretty high.
I think I would give it between 80 to 85% chance of everything going right.
Chance of success. Chance of success. It depends on your definition of success.
Oh, how likely do I think success will be? I can't actually answer that. I always assume it's not going to work. And I'm always surprised that it does. So when I think about the day of the launch, I get a stomachache. And I say to myself, I'm never doing this again. It's too hard, it's too terrifying. But then I think about, well, what if it works? What if we really have put enough attention into the details? What if we have really gotten it right? What if things really do go well? The scientific output we can get from this instrument makes it worth it. But I am afraid every day. Well, SuperBIT has been an amazing collaborative effort, obviously from my incredible hardworking graduate students at University of Toronto, but also the amazingly talented team at Princeton University led by Bill Jones and Steve Benton, and the incredible astronomers from Durham led by Richard Massey and JPL. None of this is possible without funding from both the Canadian Space Agency and NASA. And also, we just have to say thanks to the incredible flight support from both the Kenneth Stratus team for our 2 test flights out of Timmins, and from Columbia Scientific Balloon Facility in Palestine, Texas, who's given us 2 amazing test flights and then this incredible, unparalleled superpressure balloon flight. May SuperBIT fly for 100 days. It will never work. We should quit now. It will never work. Once one of my graduate students pointed out to me that those are not particularly encouraging words.
Depends on how you say them.